We'll begin by revisiting example 1 from section 2.1. We are again interested in finding the resultant of three known forces, but we'll use orthogonal decomposition to find the resultant components and then describe the resultant vector. We'll do this first using a traditional xy coordinate system, then repeat the exercise using a tangent normal or TN coordinate system. In this case, the tangent direction will be along the incline supporting the I-beam, and the normal direction will be normal or perpendicular to the incline. This normal direction also is aligned with the beam's axis. You may wonder why we would be interested in resolving components into this tangent normal system. In a support like the one shown in the figure, there will be some means by which the beam is anchored into the support, and its structural integrity along its support will likely vary quite a bit compared to transverse to the support. The failure load for dislodging the beam normal to the incline will be very different than the failure load for dislodging it tangent to the incline, so knowing the force components in the tangent normal direction could provide some insight into which failure mode is more imminent. Once again, we can declutter our figure by removing everything except the three forces. Before we resolve the forces into components, let's take a moment to label the four quadrants 1, 2, 3, and 4 in our xy coordinate system. Force F1 is in the first quadrant, so both its x and y components are positive. Force F2 is in the second quadrant, so its x component is negative, but its y component is positive. Force F3 is in the third quadrant, so both its x and y components are negative. Note also that we have three acute angles in the figure, but only the 45-degree angle is defined off the positive x-axis. It's important to keep this in mind when we use sines and cosines to define different component magnitudes. In our xy coordinate system, we can write our force F1 as 600 newtons times the cosine of 45 degrees in the I direction plus 600 newtons sine of 45 degrees in the j direction. And the numbers turn out to be 424.3 newtons in both x and y. For force F2, we have an angle defined off the vertical axis, so the sine of that angle will give us information about the x component, and the cosine of that angle will give us information about the y component. We're going to have now F2 is minus 800 newtons sine of 60 degrees in I, and plus 800 newtons cosine of 60 degrees in j. And the numbers turn out to be equal to minus 692.8 newtons in I and plus 400 newtons in j. For force F3, we have a 75-degree angle defined off the negative vertical y-axis. So again, the sine of that angle will give us information about the x component, the cosine about the y component. So now we're going to have, for F3, minus 450 newtons sine of 75 degrees in I, and minus 450 newtons cosine of 75 degrees in j. And those numbers turn out to be equal to minus 434.7 newtons in I and minus 116.5 newtons in j. To find the resultant, we again just add all the I components together and all the J components together to get the components of the resultant. So we have 424.3 minus 692.8 minus 434.7 newtons in I, and we have plus 424.3 plus 400 minus 116.5 newtons in J. And those results turn out to give us a resultant that's equal to minus 703.2 newtons in I plus 707.8 newtons in J. The magnitude is just the square root of the sum of the squares of those components, and that turns out to be equal to 998 newtons. The angle that this makes with the x-axis is the arctangent of the y over x components, and we can see that this ratio is just about equal to -1. So again, if we use our calculator, it will probably tell us that theta is minus 45 degrees, but we can see from the result here that with the positive y component and negative x component, this is going to be in the second quadrant, and the appropriate angle here would be 135 degrees. So we can say our resultant is again 998 newtons at an angle of 135 degrees off the x-axis. Now consider the same problem in our tangent normal system. We can first use the information in the problem statement to define appropriate angles off the tangent normal axes. Force F1 is directly aligned with the tangent axis. Force F2 makes a 60-degree angle with the y-axis, but the normal axis is 45 degrees off the y-axis, which means that the angle between F2 and the normal axis is 15 degrees. Force F3 is 75 degrees off the negative y-axis, which is 105 degrees off the positive y-axis. Again, because the normal axis is 45 degrees from the y-axis, the angle between F3 and the normal axis is 60 degrees. Once again, before we resolve the vectors into components, let's sketch the four quadrants. 1, 2, 3, and 4, and make a note of which components are positive and which are negative. Force F1 is aligned with the positive t-axis, so it will simply be 600 newtons along the unit vector that points in the tangent direction. Force F2 is in the second quadrant, so it will have a negative tangent component and a positive normal component. Force F3 is also in the second quadrant, so its component signs are the same as those of F2. F1 is simply 600 newtons in the tangent direction. For F2 and F3, we have angles defined off the positive normal axis, so we'll use the sines of those angles to get information about the tangent components and the cosines to get information about the normal components. We're going to have now minus, for F2, minus 800 newtons sine of 15 degrees in the tangent direction, and plus 800 newtons cosine of 15 degrees in the normal direction. And those numbers turn out to be equal to minus 207.1 newtons in the tangent direction and plus 772.7 newtons in the normal direction. For F3, we have minus 450 newtons sine of 60 degrees in the tangent direction plus 450 newtons cosine of 60 degrees in the normal direction. And those numbers turn out to be minus 389.7 newtons in the tangent direction plus 225 newtons in the normal direction. Again, we can collect the tangent and normal components separately to find the resultant. Here we have 600 minus 207.1 minus 389.7 newtons in the tangent direction, and we have 772.7 plus 225 newtons in the normal direction. This ends up giving us a very small component, 3.2 newtons in the tangent direction and plus 997.7 newtons in the normal direction. So we could find a resultant again as the square root of the sum of the squares, but the tangent component is essentially negligible, and this ends up giving us 998 newtons. We could define an angle phi off the tangent axis as the arctangent of the ratio of the normal component to the tangent component. And this is going to be obviously a very large argument. The arctangent of infinity would be 90 degrees. This ratio is something like 312, and so if we take the arctangent, this actually turns out to be something like 89.8 degrees. Now, if we were measuring this off the positive x-axis as theta, it would be phi plus 45 degrees, since the tangent axis is 45 degrees off the x-axis. So this is, again, 135 degrees off the x-axis, and our result is entirely consistent whether we do this in the xy coordinate system or the normal tangent system. The appropriate point here is that it doesn't matter which orthogonal system that we choose. As long as we are resolving components into orthogonal directions, we can collect all the components in one direction separately and add those together to get the resultant in that direction, and then separately add all the components in the mutually orthogonal direction together to get that resultant component. And we'll get the same result no matter how we do this. In our second example, we examine something quite simple in order to make the point that there are shortcuts in notation that appear throughout many textbooks, including this one, and that you should be prepared to interpret that notation so that you can write vector components down by inspection. Instead of specifying the angles vectors make with specified axes, as in example 1, vector orientation may be provided graphically with rise over run symbols as shown here. On the left, in part A, the symbol indicates a rise over run of 4 over 3. An inefficient way of using this information would be to find the angle corresponding to this as, for instance, the arctangent of 4/3, which happens to be 53.13 degrees, and then take the cosines and sines of this angle to find the force components along x and y. Instead, remember the definitions of cosines and sines. The cosine of an angle is the ratio of the adjacent side to the hypotenuse. The sine of an angle is the ratio of the opposite side of the hypotenuse. In this case, we're given information that allows us to find the hypotenuse of these right triangles very easily. If we have a triangle of lengths 3 and 4, we can find very quickly that the hypotenuse here is 5. And as one other common illustration, if we have a triangle with one side equal to 5 units and the other side equal to 12 units, the hypotenuse can be very easily shown to be 13. The 3, 4, 5 triangle notation in part A is telling you, by inspection, that the cosine of the angle made between the vector and the x-axis, we can call it here theta, the cosine of theta is 3/5, and the sine of theta is 4/5. Therefore, you should write down by inspection that the force vector F is 100 newtons times the cosine of theta, which is just 3 over 5 in I, and then 100 newtons times the sine of that angle, which is just 4 over 5 in J. Again, that's just making use of the definitions of cosines and sines as ratios of adjacent or opposite edges to the hypotenuse. Similarly, in part B, we should be able to write down that the force P is 100 newtons times 5 over 13 in I plus 100 newtons times 12 over 13 in J. One more point about these results is worth mentioning. We could bring the common 100 Newton magnitude out front and write the force in part A as 100 newtons times 3/5 I plus 4/5 J, which we could also think of as 100 newtons times a unit vector for force F. Similarly, our force P could be written 100 newtons times 5/13 I plus 12/13 J, or 100 newtons on a unit vector that points in the direction of P. You can easily verify that the magnitudes of the unit vectors are 1 and neither has any physical dimensions. In 2 dimensions, if we know an angle defined off an axis like theta is defined here off the x-axis, we can write down immediately that the unit vector that goes with that is cosine theta in I plus sine theta in J. Defining unit vectors is often a very important step preceding the establishment of equilibrium, and we will get some insight into that in the next example.